This presentation is on advanced reactions and all the other topics that you would need to go through to understand how to do all the reactions for the course. And we will also go through a series of reactions so you can see how I would approach them. So one of the tougher types of reactions for you guys, because you haven't had a lot of exposure to it, are oxidation reduction reactions or redox reactions. So here's another little helpful hint for you, is that Leo the lion goes grr. So if you lose electrons, it's oxidation. If you gain electrons, that's reduction. Or oil rig, where oxidation is losing electrons and reduction is gaining electrons. So here's an advanced redox reaction. In this reaction, it's not simple pure element becomes an ion, ion becomes a pure element. Sometimes they just change their oxidation numbers a little bit. So copper on the left is obviously a solid pure metal by itself. On the right, it's also going to be part of a compound, so it must be an ion then, so it must have lost electrons to become oxidized. So then the question is, who was reduced? Because if you have one, you have to have the other. So the hydrogen on the left is a +1 in the nitric acid, and on the right in the water it's also a +1, so it's not the hydrogen. And the nitrogen on the left is going to be in the nitric acid. If hydrogen's a +1 and oxygen's a -2, that gives us 3 oxygens -6 +1. So the nitrogen and the nitric acid must be a +5. If we go to the right side, we see nitrates with the copper, so that's the same nitrate that's in the nitric acid, so that hasn't changed. But if you look at the nitrogen monoxide at the end, oxygen's got a -2, which means the nitrogen then is only a +2. So nitrogen is the thing that's being reduced because it's going from a +5 in the nitric acid to a +2 in the nitrogen monoxide gas. So now we figured out our two halves. So we have the net ionic equation with the oxidation numbers. We break it into the half reactions, which we've now determined what they're going to be. And then we have to balance the elements other than hydrogen and oxygen. And we also have to balance the electrons. Since copper is losing 2 electrons and the nitrogen is gaining 3, then the copper is going to have to do it 3 times for every nitrogen's 2. And then we have to change the coefficients to balance the elements other than oxygen and hydrogen. And then we balance the oxygen by adding waters, and we balance the hydrogen by adding H pluses to the other side. And then if it's in a basic solution, we'll add 1 hydroxide to both sides of the equation for each H plus, and then we'll get water out of that and then cancel the waters. So here's an example where we can show this whole thing beginning to end. So we're starting with chromium and we're reacting it with some sort of nitrate, and the chromium is going to end up becoming chromium ions, and the nitrate ends up becoming nitrogen monoxide. And it's in an acid solution. So our oxidation step is the chromium losing the 3 electrons. Our reduction step is the nitrogen gaining the 3 electrons. So this is similar to the copper reaction we just looked at. Since the chromium and the nitrates are both trading 3 electrons, we don't have to do any other balancing for the electrons. So we're going to balance the oxygen, and then we balance the hydrogen. So the only half reaction that has the oxygen is a reduction. So we add the water to the right side of the equation to balance all the oxygens. So now there's 3 oxygens on the right. And then we have to add the hydrogen ions to the left side of the equation because we added 4 hydrogens with the water. So that balances the oxygens and the nitrogens. So we add up the 2 half reactions, and so the overall reaction is this, and this is the net ionic equation. In another example, we start with phosphite and permanganate, and it turns into phosphate and manganese dioxide, and this happens in a basic solution. So our oxidation step is going to be the phosphorus going from a phosphite, it's 3 oxygens, that's -6, but it's -3, so the phosphorus in phosphite is +3, and in phosphate it ends up being +5, so that means it's losing 2 electrons, and then we already balanced the oxygens with the phosphate and the phosphite by adding a water to the left and the hydrogens to the right. For the reduction reaction, we have the permanganate turning into the manganese dioxide, so in the permanganate, the manganese is +7, and in the manganese dioxide it's +4, so that means we had to add 3 electrons. And then to balance the oxygens, we put 2 waters on the right side, and then we have to add 4 hydrogen ions to the left to balance that. we see that the phosphite to phosphate is losing 2 electrons, and the permanganate to manganese dioxide is gaining 3, so we have to multiply the phosphite reaction by 3 and the permanganate reaction by 2. So that's what I did here. And so now we add these two up, and we get this. But now we see that we have hydrogen ions and waters on both sides, so we have to cancel the 3 waters on that side and the 8 hydrogen ions on that side with the 6 and 4 on that side. So what we end up with then is this, where we have 2 leftover hydrogen ions on the left and 1 leftover water on the right. But then we're in a basic solution, so we have to add 2 hydroxides to both sides to balance and cancel out the hydrogen ions on the left. And in the process of doing that, we get 2 waters on the left side, which can cancel with the 1 water on the right. And so we end up with this as our final equation. These are very long, drawn-out problems. They're complicated. You have to be very careful with your math that you do and keeping track of how many of each thing there is. So just take your time and be very methodical with these, and you'll do fine. So why do we care about redox? Redox can occur in one place, or we can split them up into separate cells. And in the process of doing that, since we connect them with the conductor, we allow the electrons to flow, and that's the energy that then we can use for things. So when we have a voltaic or a galvanic cell, that's where it happens spontaneously. So this would be like a battery. And where we have an electrolytic cell is where we force it to occur by putting energy into it, electrical energy into it, and that's how we can plate things or recharge batteries. The places where the electrons are exchanged are called the electrodes, and they are dipped into the electrolytes or the solution with the compounds in them. So the electrode where reduction takes place we call the cathode, because the cations tend to move towards that electrode, and the electrode where oxidation takes place is called the anode. And then we put a salt bridge where we combine the two, and that just allows ions to move. So that's just a porous membrane that separates the cells, but then will allow the ions to move to keep the charge in the cell balanced, because you can't end up with a net charge on one side versus the other. So here's a picture of a standard voltaic cell where we have zinc dipped into a zinc nitrate solution or some sort of zinc solution, and copper, pure metal, dipped into a copper solution, and the salt bridge is just sodium nitrate, which allows the movement to ions. And then you can see how the electrons are going to move from the zinc to the copper, and that's what creates the voltage. So at the copper electrode, you have copper ions from solution picking up the electrons from the electrode and attaching itself to the electrode, so that electrode gets bigger. And on the zinc side, the electrons are being pulled out of the zinc, and so you end up with zinc ions in solution, so that electrode actually gets smaller, and there's your 2 half reactions. But we'll come back and do a lot more of this later on when we get to the electrochem chapter and cover it completely. So let's do some practice. A strip of zinc is placed in a solution of nickel 2 nitrate. So you have a pure substance going into a compound. So this is going to be what we used to call a single replacement reaction, but now this is a redox reaction, because the zinc is going to lose electrons and the nickel is going to gain them. So when we write it out, we have zinc plus nickel 2 nitrate yields zinc nitrate plus nickel, but we have to write the net ionic equation. So the zinc is going from 0 to +2, the nickel is going from +2 to 0. The nitrates are staying exactly the same, so we can remove them because they're unchanged. They're what we call spectator ions, so we remove them and end up with this as our balanced equation. Here's another one where we have ethylene or acetylene, which is C2H2, and it's burned in air, so this is a combustion reaction. So you take that, react it with oxygen, and you get carbon dioxide and water. So there is the reaction when it's all balanced. You end up having to double it so you can get an even number of oxygens on both sides. If you did not double the acetylene, then you would end up with an odd number of oxygens on the right side and would have to use a fraction or something on the left, which you're not allowed to do. So we double the acetylene so that we end up everything being whole numbers. Solid calcium carbonate is added to a solution of ethanoic acid, acetic acid. So acetic acid is a weak acid, and calcium carbonate is a solid, so we have to write them completely out. So it gives us this, and it's going to be what we used to call a double replacement reaction, but now we call it a precipitation reaction, where the calcium is going to join with the acetate and the carbonate is going to join with the hydrogen. So what we make then is calcium acetate, which is soluble because all acetates are, so we have to write them as ions. And then the hydrogen goes with the carbonate, makes carbonic acid, which gives us water and carbon dioxide. You just need to know that carbonic acid always breaks down into water and carbon dioxide. And since the carbon dioxide leaves, that's why this is a precipitation reaction. And you have to write the calcium acetate ions out because there are no spectators here because it started as calcium carbonate and it started as a weak acid. And so you can't leave anything out. Lithium metal is strongly heated nitrogen gas, so this is going to be a synthesis reaction where the lithium and nitrogen are going to come together to make the compound. So this is going to be an ionic compound. And so your formula for lithium nitride is going to have to be Li3N to balance the charges. And don't forget that nitrogen's diatomic, and then the rest of it is just making sure you balance correctly. Sulfur trioxide gas is bubbled into a solution of sodium hydroxide. So this one's a little interesting because you're not exactly sure what's going to happen, but if you're dealing with a molecular substance, it usually tries to become ionic. So sulfur trioxide with the sodium hydroxide will make sodium sulfate and water. All right, so the sulfur trioxide gains the oxygen to become the sulfate ion. When we write it out as ions, the sodium now is a spectator, so your formula ends up being the sulfur trioxide plus 2 hydroxide ions gives you sulfate ions and water. And the last one is we have equal volumes of 1 molar solutions of lead 2 nitrate and magnesium iodide are combined. So this is a precipitation reaction. And so when we write it all out, we get lead ions plus nitrate ions plus magnesium ions plus iodide ions gives us a lead 2 iodide and nitrate and magnesium ions. And the nitrates haven't changed and the magnesium ions haven't changed, so they are our spectators. Only the lead and the iodine has made a solid now and went from being ions into a compound that can't come apart. So that is our whole reaction. So we'll practice more of these, but these are the types of things that you have to be able to go through on your own.